Alright, in this problem we're going to be doing parameter estimation. Physics-based models give us an idea of what's going on. In physics, we're trying to replicate what's actually occurring, just like that, the physics. Because of that, though, we may have different characteristics than what we assumed in our physics-based model. For example, our heat capacity may be slightly off because of material construction. Our ambient temperature might be slightly different. One that comes to my mind oftentimes is the convection term. That convection term is usually found by regression in and of itself. And so if we have different air than with the regression when that was regressed, we're obviously going to have a different performance. So that's what the goal here is that we decide on some values within the physical system that we think we can change, that we might regress to fit our model better, and then control based on those better fitting values, thinking that we're reflecting what's actually occurring in the system more. So let's go ahead and look how we do that. Before we do so, I want you to take a moment, pause or don't pause, I'll take a moment and pause just briefly. What values within the physical model do you think we might want to regress and change? Alright, that's a moment enough. So we're going to clear all, close all, CLC as normal. This get active helps us store the directory that the file that we're in right now is. And that's so that we can save the data from the step test we're about to do. And then if we've already done it, we don't need to rerun this 14-minute test. We can just continue on our way and work on the regression portion. So this is just to save you. If you've already done this, you're not expected to have the value off the app, to have this step response CSV off the bat. Now I've already tested this. I already have the CSV. For the sake of time, what's going to happen is we'll still set T1, we'll still set time, and we'll still set what the heater set point should be. Then I'm going to try and read that step response.csv. Because I have it, it should work. Let's go ahead and we'll just try. There we go. So we have in one column the time, I believe. Time is in the first column. T1 is in the second. Now that doesn't look right to me. That doesn't look like a T1. Oh, 10 to the third times. 10 to the third. Okay, yeah, that makes sense. 10 to the third, so it's time 100, or it's 1,000. Now I'm confused. 1, 2, 3. 10 to the third here makes sense. That makes that a 0.1. And here, if that's 25, it still makes decent sense. Maybe it's 10 to the second, or just 100 times that one. We'll see soon enough when we graph it. If not, we're going to connect to the lab, start our timer, and do something like we've always done. We're going to record the time, we're going to record the temperature, we're going to set the heater, and then we're going to start plotting it. Then we're going to close it and clear lab. Finally, we're going to save and time in T1. And then lab.off and clear lab if there is some error. So then we're going to fit an FOPDT to the data that we've regressed. So the way we do that is first we make a vector with all the parameters we want to regress. For an FOPDT, it's going to be the gain, it's going to be the process time constant, and it's going to be the dead time. A second order plus dead time model could also be more accurate, and we'll look at that later. So first we create an array and store these three values. You can see this is actually a vector. It's 3 rows, 1 column. The next thing we want to do is set our initial objective function so that we know if we've improved. And we do this with our objective function. So let's scroll down and find that objective function. Here's dy dt. That's the equation for FOPDT slope. Next we have simulate FOPDT model, which will simulate the FOPDT by unpacking the 3 parameters. And then it will likely, right here, you see, will integrate based on that slope at any given time, based on the parameters, as well as U, which is the heater value, the input, as well as the T, and then the what the temperature is at that moment. And so our objective function uses sim model, which is this function right here, to simulate what the FOPDT parameters would be and what the temperature would be of those simulated parameters. Then we take the sum squared error times 1,000 so that we make it even more accurate. We're able to see the gradient more and the change in error more if we multiply it by 1,000. So we take the difference between what the FOPDT calculated that our temperature should be based on the coefficients we gave it, and then we get the sum squared error of that. And now our goal is to minimize the difference between these two models, or I should say, our experimental data and our physics-based model. Excuse me, not our physics-based model, our FOPDT. Excuse me. So let's look. We're going to take FOPDT parameters, and we're going to use fmin search. We've done that before. It's been a few weeks. So we use fmin search. We're naming the function, so we use the @ symbol, and we're making it an anonymous function technically. So we give it first x, and then our objective function takes x, which is those parameters, then time, q1 and t1, as well as the initial guess. Then the optimized objective function we have as well. So if the initial, it's 2.4 times 10 to the 8th. And our optimized one is 2.9 times 10 to the 6th. Now let's look our FOPDT parameters. The first one's going to be k, so the gain, and our gain is 0.58. So for every, let's look at our system. It's a relationship. The gain is a relationship in to out. So the steady state temperature, when everything's done, the temperature will increase 0.58 degrees for every percentage increase in the heater percentage. Tau m, we guessed 120. It's actually 128. That's not a bad guess. And finally, we guessed our dead time was 10 seconds. Turns out we regress it to be more like 21. So let's look at this graph a little bit more. It's even hard to see. If you look really close, there's a black line, which is our regressed data. Our regressed line. These red dots are the measured data, and that's good. Dots are always good for experimental points. And then our dashed line is our initial guess. So you can see we definitely guessed too high for an initial slope. Now what's going to happen is we're then going to control based on this. Now that I think about it, we're gonna test how good it is by using our physics-based model. Now we're gonna now fit the physics-based model with optimization and fit these constants rather than an FOPDT. So again, M is the mass. We got heat capacity, temperature, and heat transfer coefficient. This is a single heater, so we're assuming that we're not receiving any heat from it, and it's the same temperature as the rest of the ambient. We're going to use fmin_con, which performs constrained optimization, and it does that in the form ax is less than or equal to b, or how we pass the constraints. So we're going to regress two things. We're going to regress first that lumped convection conduction heat transfer parameter, and the second one, that kind of the gain, the relationship between percentage into the heater and the wattage we get out. So let's look at our constraints now. Ax is equal to b. You'll notice this is a vector. This is a column vector. And you'll notice that x is as well a column vector. So we've got u and alpha. And so u times this column times alpha, u times the first column of A, plus alpha times the second column is going to equal the element of B. For example, u times -1 is going to equal -1. And that's because it's equal to itself. I think we're saying, let me think that through. Negative u is equal to -1. Positive u is equal to 20. Oh, because we're doing up, we have this, I do these things just a couple hours ago and then I forget. So ax is less than or equal to b. Well, if we want to set a minimum and a maximum, we'll use the negative. So u times -1 is less than or equal to -1. So if we multiply both by -1, then u is less than or equal to 1. Let's go on to the second one now. U times 1 is less than or equal to 20. So u is somewhere between 1 and 20. Alpha, similar thing, minimum, maximum. So the minimum is going to be 0.001 and the maximum is going to be 0.05. So we're saying that it's between 1/10 and 50 watts is the output. That's quite a range, but it gives it, I think we'll be able to narrow it down. This time our objective function is objective energy balance. Let's go ahead and look at that function. We have our objective, then we have heat here. Heat is the first principles model where we take our parameters and we calculate the change in heat over time. And then our function sim energy balance will take our parameters, take our time, take the heater setting at any time, and take the predicted value at any time. Or sorry, not the initial condition. So these are the actual measured values. And then we will simulate with ODE 45 again. We'll integrate the change in temperature at each point because it builds off the previous point. Then we'll take our objective function, similar to the last time. We'll use our sim energy balance, our sim function, to create the model for all the points. And then we'll use our objective function to do the sum squared error between the model and our regressed and our measured data. I'm sorry, I can't talk tonight. Finally, we will graph both, or we'll get the results of both using this sim, and then we'll plot as we did before. Let's look at these graphs. We can notice right off the bat we're actually much closer than our initial guess with the FOPDT. We start at a good temperature because we reference it, and we go up. You'll notice we still don't have the dead time built in, but our degree of our gain is pretty accurate. It then falls, and again, it falls a little bit faster than we'd think before, but the magnitude of our changes are much more in line. Even our initial guesses are pretty in line. So there you go, that's how we regress the parameters. From this, we're able to look and we can say, okay, well, these are FOPDT parameters, excuse me, it's because I scrolled over here and that messes everything up. So our objective function was a little bit higher than the FOPDT, it looks like, 1.3 times 10 to the 6th, whereas this one was 2.9 times 10 to the 5th. So almost a degree of a magnitude of, an order of magnitude different. Look at that, that's right on. But let's look at our transfer, or our coefficients that were regressed. You'll see regressed heat transfer coefficient U is 3.8. I don't believe that they're both 3.8. So let's look. I bet there's a problem with our print statement, or our display statement. We'll do Control Z right here. That should be 2. So let's go ahead. I'm going to run this section again. Unrecognized variable, get IP options. Error in fmin_con. Well, I guess we'll have to figure this out. The error in the fmin_con is because we have an error in the options. My guess is it's because of this right here. We're going to go ahead. I'm just going to run it from the beginning. I don't think I ran it from the beginning. Run. That was run all. There we go. So I'll read it again. Hopefully this makes you feel better about when you have errors. TCLab read from data. Here we go. We're regressing the FOPDT parameters right now. You notice this takes time. fmin search especially is unconstrained, and so it's going to be looking and performing optimization. If you remember your calculus classes, what's going on with optimization, it will try a few points and it will see the gradient of error, our objective function, and it's going to try to make the error as small as possible. And so it's going to follow the gradient as error decreases within the 2 manipulated variables, or 3 in the FOPDT case. So may take a second. I'm going to go ahead and just pause it just for your sake, and we'll pick it up at the end. Alright, I figured out what it is. I don't have the optimization toolbox installed, and so I won't be able to do constrained optimization until I install that. So I'm glad we're all here together. We can figure this out. So I'm going to go ahead and we look here, install app. It's not an app. Package app. We're not packaging something. We're going to get more. And so I'm going to go, I believe, at home, right about here. I know I saw that thing. We could also just Google it online. MATLAB optimization toolbox. But I know it's around here somewhere. Add-ons. Go add-ons. I guess we'll just go add-ons. Add-on Explorer. Optimization. Optimization toolbox, and it's included in my license. What do you know? So we'll go ahead, we'll install that, and we'll go ahead and do it again. Alright, after installing the package and restarting MATLAB, here's our results. We actually were able to perform better. Our optimized objective function was 1.3. Our regress at 1.3 times 10 to the 6th. Our regressed heat transfer coefficient was 3.8. And our regressed heater factor is 0.0079. And there you have it. So let's move on now to 2 heaters in the next section.